I want to derive this famous formula, which is also known as Stokes' law. In particular, this is the formula Fd equals 6 pi mu Rv. And we are talking about the frictional force acting on a spherical object. So you can think of a sphere, and we have very small Reynolds numbers, which means that we can neglect the inertial forces and the kinetic terms, which are proportional to v squared. So I will talk about it also later. We have already derived in previous videos the equations also known as Navier Stokes equations or hydrodynamics equations. We will use those equations to derive this law, and we will skip some calculations, but those calculations will be done by means of MATLAB. So I will use MATLAB to carry out some derivatives and to find the solution to some problems, some equations. You can see here that I have prepared the script, and we will also analyze this script in order to understand much more deeply why those formulas arise. This is important because I don't want to do too many calculations. We will do some, but if we did all these calculations here in this script, it would take too long. And this is why it would be useful to use MATLAB or any other calculator, let's say, to solve this problem. But we will use this later. First, we will have to set up our problem and then put us in a position to be able to solve the equations and understand the meaning of the equations. And finally, when our problem is set up completely, we will use this script, but this will come later. So let me use my whiteboard here, and let's start from Navier Stokes equation. So I will take this as a given because I have derived these equations previously, and basically what we are going to do is we are going to consider no external forces, and also the inertial forces, as I said previously, are negligible because we want to consider a small Reynolds number. So that's also another important point. Let's start with our equation. So we write the gradient of the pressure equal to mu, which is the coefficient of viscosity. In previous videos, I've also called it K because it was Einstein's notation. But in this case, this is not about any Einstein's paper, so I'm going to call it mu. And then I have the Laplacian of the velocity, which I will call u vector. This is the vector of velocity, u bar, u arrow. And then, since the fluid will be considered as incompressible, we have that the divergence of the velocity is equal to 0. So these are the two equations. Now we define another vector, omega, which is known as vorticity. So this is the vorticity, and it will be useful to solve the problem. So omega is equal to the curl of the velocity. This is a definition. You take this as a definition. And now let's consider the curl of omega. This is the curl of u, like this. Now we can show by using index notation that this is equal to minus del squared u. So it's minus the Laplacian of the velocity. And I'm going to do it in a few steps. If you don't know index notation, never mind, it's not so important, but I'm going to do it here. So this can be written as, so if I have a curl, I can use the Levi-Civita symbol. I have epsilon ijk, and then I have the derivative with respect to the jth component. I will call it dj, so it's the derivative with respect to this one. And then I have the vector omega written with respect to this index here. So that's omega k if you want, but omega k is equal to this, the kth component of this. So let me rewrite it as, here we will have another epsilon because I have another cross product, and then this will be epsilon k. It will start with k, and then I have other two indices, L and M, dl um, and this can be written as epsilon I j k, epsilon L n k. So basically here you also have to sum over j, over k, over L, and over m, and also over k here. You see that you also have to sum over k. The only index over which you're not going to sum is I. This is the free index. And then here I have dj, dl, um. So you can see that they have changed the order between these three indices, because the first order was KLM here, but you can put M first, and then you consider a positive permutation, which means that after M you have KL, and then you can do another permutation. So this is a positive permutation, MKL, for example, but you can also permute it in this way. You are going to put L here, and then you have MK, like this. So this is another positive permutation, and you can do this, right? But in this case, I can rewrite the product between these two Levi-Civita symbols as a product of Kronecker deltas, and there's a sum of these products. So I have delta IL, delta JM, minus delta IM times delta JL. This is a simple formula that you can easily derive. And then when you multiply by these deltas, you can derive the formula like this. You have delta I del M um minus del J um. And this is simply equal to the gradient of the divergence of the velocity minus del squared u. But the divergence of the velocity is 0, so this is minus del squared u. Simple as that. Now that we have shown that indeed the curl of the vorticity is equal to minus del squared u, we can rewrite this formula above, because we can rewrite it as the gradient of P equal to minus mu the curl of omega, like this. And if you take the divergence on both sides, the divergence of the curl is 0, and therefore you get that the Laplacian of the pressure should be equal to 0. This is an equation that should be satisfied. And then you can also find that if you take the curl on both sides of this equation, you have that the curl of a gradient is equal to 0, right? And so we can actually take the curl of this expression here. You have the curl of the gradient, which is 0, and then you have mu del squared curl of u. So this operator can be put before the Laplacian. We can change the order between them, because they are partial derivatives after all, and we can always change the order between the partial derivatives. But what is this? The curl of u? Well, that's simply the vorticity omega. So we also have that the Laplacian of the vorticity is equal to 0, the 0 vector if you want. Now, what we are going to consider is a sphere, because Stokes' law is related to considering a sphere in a liquid, and the velocity field far from the sphere is assumed to be uniform. So this is the condition. We have a sphere somewhere here, and we will consider the origin to be at the center of the sphere. Then we have the z-axis, which goes this way, and then we have the x-axis and the y-axis. And the velocity field far from the sphere will be homogeneous, so it will be constant, and it will be along the z-axis. And we will call this u infinity. U infinity will be the velocity along z. So the velocity u at infinity for large distances will be 0, 0, u infinity, or just u equal to u infinity. Doesn't matter. So u without the arrow will be u infinity, and it can also be indicated like this, u. For example, in the script, in the MATLAB script that we will see, it will be called u. But in this case, while doing the derivation, we will call it u infinity, just like this, right? And we want to understand what is the function u also near the sphere. That's important. And we will use cylindrical coordinates, not spherical. So let me stress this. Even if this is a sphere and there is some kind of spherical symmetry if you want, we are going to use cylindrical coordinates. Let me write it, cylindrical coordinates. So the z-axis is passing through the center of the sphere, while r, the radius r, is measured perpendicular to the z-axis. So this will be simply the square root of x squared plus y squared. Or maybe in general in spherical coordinates you also have rho, which is the square root of x squared plus y squared plus z squared, which is the distance from the origin. But in this case we are considering r. And so it is assumed that the flow goes along z, this flow here. And because the flow is symmetric with respect to the z-axis, it is independent of the angle theta, the azimuth angle theta. So the velocity along theta will be equal to 0. Because there is this symmetry with respect to the z-axis, this means that if we take a look at the sphere from above, so this is the origin and it is the z-axis coming out of our whiteboard, x, y. Now, the radial distance, so this is the distance, for example, of the radius, and here we have the unit vector r, which goes along the radius, and it is also normal to this circumference. And I mean, we are considering this section on the xy plane. And then a vector which is perpendicular to r, this one here, defines theta. So it defines the vector theta, and this is the angle theta here. So the velocity along theta will be 0, because otherwise we will lose this symmetry with respect to our z-axis. We are considering a sphere, and the flow goes along z, which means that u theta should be equal to 0. So this is one first result that we can simply obtain by our reasoning. So the first result is u theta equal to 0. And then now we can define a so-called stream function such that, so the function will be called psi. And this function satisfies these relations. uz is equal to 1 over r d psi over dr, and you have to take this as a definition, and I will motivate this definition in a moment. And we also have u along r is minus 1 over r d psi over dz. So these are the three components of the velocity written with respect to psi. So u theta is the simplest because it is equal to 0. But these other two, uz and ur, are defined with respect to psi. Why can I do that? Well, remember that we have to comply with the condition that the divergence of the velocity is equal to 0. And this divergence can be written in Cartesian coordinates as dux dx plus duy dy plus duz dz equal to 0. Now, in order to see if this condition is satisfied, also in cylindrical coordinates, we have to rewrite the divergence in cylindrical coordinates. So that's important. And let's try to understand if indeed the divergence of u is 0, because we must satisfy this condition. But first we have to transform our divergence into cylindrical coordinates. And this will be quite easy because duz with respect to z will not change. This will be the same. Because in cylindrical coordinates we are just changing x and y because they will depend on r and theta, but z will remain the same. So this part will remain the same. So we have to understand how this transforms in cylindrical coordinates. Let's consider a function f in general. So we have dfx dx plus dfy dy that we want to understand how to change going from Cartesian coordinates to cylindrical coordinates, where the vector f is defined as fxi plus fyj, and these are the unit vectors along x and y respectively. But this vector f can also be written in polar coordinates. In this case, I'm using the word polar because we are not considering the z-axis. If we consider also the z-axis, I should call it cylindrical system. Okay, but doesn't matter. So if we go from xy to r theta, we are going to a polar system. And here I have fr r hat plus f theta theta hat, like this, where r is simply equal to the cosine of theta I plus sine theta j, whereas theta will simply be the derivative of this vector with respect to theta. So it is minus sine theta I plus cosine theta j, and this is dr d theta, dr at d theta. And now if you substitute these expressions, this one here, in here, you can find the relation between fx and fx fy and fr f theta. So if you substitute, you have fxi plus fyj equal to fr cosine theta I plus fr sine theta j minus f theta sine theta I plus f theta cosine theta j, like this. And from here you find that fx should be equal to, so since fx multiplies I, all those multiplying this unit vector I will sum together to obtain fx. So fr cos theta minus f theta sine theta will give me fx. Since I and j are independent, they are perpendicular to each other. So we can do this. We have fr cosine theta minus f theta sine theta, whereas fy will be fr sine theta plus f theta cosine theta. And then we also have to change the derivatives. So we found an expression for fx in terms of theta, fr, f theta, and fy as a function of fr, f theta, and sine theta. So this is what we want. We want to go from the variables x and y to the variables r and theta. So we also have to change these derivatives. And how to do that? Well, we have to use the chain rule. For example, the derivative with respect to r is equal to d over dx, dx over dr, plus d over dy, dy over dr. And this is simply equal to cosine theta d over dx, because the derivative of x with respect to r is cosine theta, because x is equal to r cosine theta and y is equal to r sine theta. And then here we have plus sine theta d over dy, and then We also have d over d theta. Here, let me rewrite it as 1 over r d over d theta. This becomes d over dx over d theta times 1 over r plus d over dy times dy over d theta times 1 over r, and this is equal to minus sine theta d over dx plus cosine theta d over dy. Now we have almost all that we need. In particular, now here we have a relationship between d over dr, d over d theta, and the derivatives d over dx, d over dy. We can rewrite this using matrix notation. So d over dr, 1 over r d over d theta is equal to the matrix cosine theta sine theta minus sine theta cosine theta, and then here we have d over dx and d over dy. But if we invert this matrix, which is very simple, very easy to invert because we simply have to take the transpose. Since this is an orthogonal matrix, orthonormal, because if we call this Q transpose is equal to the identity matrix. It's very easy to see. And therefore, it means that the transpose is equal to the inverse. So we can rewrite d over dx, d over dy vector is equal to the inverse of this matrix, Q, which is of course equal to cos theta minus sine theta, cosine theta, which multiplies d over dr, 1 over r, d over d theta, like this. And therefore we also find an expression for the derivatives d over dx equal to cosine theta d over dr minus sine theta over r d over d theta, and then we have d over dy equal to sine theta d over dr plus cosine theta over r d over d theta. And therefore we can rewrite dfx dx plus dfy dy. Now we have an expression for the derivatives, and we also have an expression for these two functions, fx and fy. We just have to make a substitution and do some calculations. So here we have cosine theta d over dr, this first part, applied to fx, and fx is simply equal to fr cosine theta minus f theta sine theta. Then we have minus sine theta over r, d over d theta, and still fx, which is fr cosine theta minus f theta sine theta, plus, now we have d over dy, so I put this one first. I have sine theta d over dr of fy, which is fr sine theta plus f theta cosine theta. And then we have this last derivative, so plus cosine theta over r d over d theta of fy, which is fr sine theta plus f theta cosine theta. And now you just have to do a bunch of calculations. And in this case, I will skip them because it's unnecessary to carry out these calculations. They are quite easy to do. Lots of terms will also cancel. And of course, you also have to know that cosine squared plus sine squared is equal to 1. And you will find the following expression. So the divergence of f can be written as dfr over dr plus 1 over r fr plus 1 over r df theta d theta. In this case, the function f is simply fx and fy, so I'm considering a function with only two components, fx, fy. If you have fz and you want to rewrite it in cylindrical coordinates, here you simply put dfz dz, like this, right? There is nothing major about it, but I'm considering this to be dfx over dx plus dfy over dy. And this is just a matter of simple calculations. So you can obtain it very easily from above. And this can also be written in this form because we can put together these two terms. You have 1 over r, and then here you have the derivative with respect to r of r fr plus 1 over r df theta d theta. And therefore, if we want to find the divergence of u, which has the three components ur, u theta, and uz, this is simply equal to 1 over r d over dr r ur plus 1 over r du theta d theta plus duz dz. But now this term here is 0 because u theta is 0, whereas we defined ur in terms of the function psi, and this was minus 1 over r d psi dz. Let's go back and check. You just have to check the definition here, and then you have this definition for uz. uz is equal to 1 over r d psi dr. So you have uz equal to 1 over r d over dr of the function psi. And if you substitute these expressions here, you see that we have 1 over r d over dr, and then rur can be obtained from here, so that's simply minus d psi dz, and then here you have plus r does not depend on z, so we can put it out of the derivative, so we have 1 over r, and here you have derivative with respect to z of the derivative of psi with respect to r. But you can see that this quantity here is 0, because we can also change the order between these derivatives, and there is this minus sign with this plus sign will give me a 0. Easy to see. Therefore, the divergence equation is satisfied. The divergence of u is equal to 0. But now what we are left to do is that we have to find psi, the function psi, because from the function psi we can find all the rest. We can find u, and it is also possible to find the pressure that we will see. So we need to find ur, in principle u theta, but this is 0, so we already have it, uz, the function p, and we can find all this from the function psi. Now, the other equation that we want to calculate is this one, omega equal to the curl of u. So we want to rewrite this equation in cylindrical coordinates because we are reasoning in cylindrical coordinates, and that's what we want to do. In particular, so if we rewrite the curl, this curl can be written in Cartesian coordinates in this manner. So let me put a minus sign. This is I duy dz minus duz dy plus j. Here you have duz dx minus dux dz plus k dux dy minus duy dx, like this. And we want to rewrite this in cylindrical coordinates. So here we want cylindrical. To transform this equation into cylindrical coordinates, we have to change uy, ux, but uz will remain the same because uz is still equal to uz in cylindrical coordinates because the z-axis remains the same, remains unchanged. But we need to change the derivative d with respect to y, d with respect to x, and the derivative with respect to z remains the same because, as I said, in cylindrical coordinates, the z-axis doesn't change. And then we also have to change the unit vectors, I and j, whereas k remains the same. What about I and j? Well, we can easily find I and j in terms of the vectors, the unit vectors r and theta, because we found some relations earlier. From where are they? You can see them here in particular. We have r and theta with respect to I and j. From here, you find that r theta, the vector r theta is equal to cosine theta, sine theta, minus sine theta, cosine theta, and then here you have ij. So you simply have to take the transpose of this matrix and put it here. The transpose is equal to the inverse because this is an orthonormal matrix. So ij, so let me write it below. Let me go below. Ij vector is equal to cosine theta minus sine theta, sine theta, cosine theta, and then here you have the unit vectors are theta, like this. So you get that I is equal to the cosine of theta r minus sine theta theta, and then you have j equal to sine theta r plus cosine theta theta, right? And then you also have the expression for the velocities. In particular, the velocity uy is equal to ur sine theta plus u theta cosine theta, which is 0 because u theta is 0, and ux is equal to, let me go back and check. So you can simply find them from these expressions here. Instead of f, you will have u. So ux is equal to ur cosine theta minus u theta sine theta, whereas uy is equal to ur sine theta plus u theta cosine theta. So we said ux equal to ur cosine theta minus u theta sine theta. So we have ur cosine theta minus u theta sine theta, like this. So let me rewrite the curl in cylindrical coordinates. I will substitute these expressions, and then I will leave the calculations to you, and I will give you the result. So the calculations are just straightforward. You just have to do some calculations, and you will obtain the result. So here we have minus the gradient, the curl of u. So I'm going to put this minus sign here. Alternatively, I could have put this minus sign inside these expressions, but this is the way I wrote it, so it's not really a problem. I have minus the curl of u equal to, I have I, but I is equal to the cosine of theta r minus sine theta theta, and then I have d over dz, which remains the same here, uy, but uy is ur sine theta plus u theta cosine theta. This will go to 0. And then I have minus sine theta d over dr plus cosine theta r d over d theta, which was this derivative here, d over dy is this one, and then I will apply it to uz, right? uz remains uz, it's the same. And you can already see that when I apply this derivative, d over d theta to uz, this will give me 0, because uz cannot depend on theta. Otherwise, if uz depended on theta, we would lose symmetry. You can already cancel this term. And then you have plus j, and j is equal to sine theta r plus cosine theta theta. And then here you have cosine theta d over dr minus sine theta over r d over d theta uz. This derivative here will also give a 0 contribution because we have d over d theta of uz, and that will give me 0. And then I have minus d over dz of ur cosine theta minus u theta sine theta, and this will give me 0 because u theta is 0. So I have simply inserted the formulas for d over dx and ux here, because uz and d over dz do not change. And finally, we have plus, here you have k, and then you have sine theta d over dr plus cosine theta over r d over d theta of ur cosine theta minus u theta sine theta. And here you can cancel u theta because that's 0. But in this case, you cannot cancel this term actually, because we have cosine of theta here. So when we take the derivative, this will be applied to the cosine of theta, even if also ur does not depend on theta, should not depend on theta, because otherwise we would lose our symmetry. And then we have minus cosine theta d over dr minus sine theta over r d over d theta. This will be applied to ur sine theta plus u theta cosine theta, and this will be 0, like this, where I have simply substituted the expressions for the derivatives d over dy here, ux, so this one is the velocity along x, the derivative d over dx, and the velocity along y. So I simply substituted those expressions. Simple as that. And now you have to do the calculations here that I will skip, not necessary. It is just straightforward. And what you will get is this. You get duz dr, and then you have minus dur dz times theta. So this is equal to, remember where we started from minus curl of u, which is equal to minus omega, and therefore since omega only has a component along theta, this is minus omega theta times also the unit vector theta. So we get minus omega theta equal to duz dr minus dur dz, and we have the expression for uz and ur expressed in terms of the stream function psi. So we have d over dr of 1 over r d psi over dr minus d over dz of minus 1 over r d psi dz, and this will give me the equation minus omega theta equal to d over dr 1 over r d psi dr plus 1 over r d squared psi dz squared, like this, like this. And remember that we also know that the Laplacian of omega should be 0. We also have this equation. This equation should be satisfied, and we can rewrite this equation in cylindrical coordinates. So this is one last step. So we find this equation here, and then we turn this equation into cylindrical coordinates. So in principle, we have d squared omega dx squared plus d squared omega dy squared plus d squared omega dz squared. And we have to transform these derivatives, d squared over dx squared and d squared over dy squared. And we have the formulas for those. Cosine theta d over dr minus sine theta over r d over d theta squared plus sine theta d over dr plus cosine theta over r d over dr squared plus d squared over dz squared. And all of this is applied to omega, the vector omega. You just have to take the square of these operators. So these are operators, so you have to be careful because the order cannot be exchanged. It's as if you were multiplying, for example, you have cosine theta d over dr plus minus sine theta over r d over d theta, and you simply multiply these two together, cosine theta d over dr minus sine theta over r d over d theta. So you take this first operator and you apply it to this term. So this will only act on this operator here because cosine of theta is independent of r. And then you will apply this to this. And you see that the derivative d over dr will act on this term, 1 over r. And then you will also have to take this one. It will act on this. So the derivative operator will act on the cosine. And then it will take this and it will act on this. So you will get two terms because d over d theta will act on sine theta, and then it will also act on this, d over d theta. So I will, maybe in this case I can do the steps to show you the results. So when you consider the square of this, you will get d squared over dr squared cosine squared also, but when you also square this, you will get a similar term with the sine squared. So you get sine squared d over dr squared. So you get in total d squared dr squared, and this should multiply cosine squared plus sine squared, but that's 1. So you just simply get this term. And then you have the square of this. So you have sine squared over r squared d over d theta squared. But you will get a similar term here with the cosine. So you will also have a term of this kind, u1 over r squared d squared over d theta squared. And then you will also get all the cross terms. So when this one acts on this, and also when this one acts on this. So you will get minus cosine theta sine theta over r d squared dr d theta, and then you will also have plus 1 over r squared cosine theta sine theta d over d theta, Then you will have this term acting on this one, giving rise to the following two terms, plus sine squared theta over r d over d over dr, sorry, minus sine theta cosine theta over r d squared d theta dr, and then you will get plus, so you will get something similar from this, so you will get this term acting on this, and therefore you get plus sine theta cosine theta over r d squared dr d theta, and then you will also have minus 1 over r squared sine theta cosine theta d over d theta, plus then you will have cosine squared theta over r d over dr, which arises because of this term acting on this, and then you will also have plus cosine theta sine theta over r d squared dr d theta, and finally, of course, you will still have d squared dz squared, and this is acting on omega, and this is the Laplacian of omega, which should give us 0. Anyway, if you do the algebra here, if you do these computations, if you just sum, you see that this term, for example, cancels another similar term. Here, this is a plus, so this one cancels this one. Then you also have this one canceling this one, and you can put together, for example, this one with this one, and then this one cancels this one. So you can see that the expression simplifies. You get d squared dr squared plus 1 over r squared d squared d theta squared plus 1 over r d over dr plus d squared dz squared applied to omega, and this is equal to the 0 vector. You can put together this one and this one. This gives us 1 over r d over dr r d over dr. And this omega here should also be transformed because this is omega x, omega y, omega z. So we have to change those expressions. So for example, we can take the first component along x and we can change this omega x. So in particular, we know that omega x is equal to omega r cosine theta minus omega theta sine theta. And we know that omega r is 0 because the only non-zero component is omega theta. So what we have here, if we put this formula there and we take the derivatives, what we get is the following. We get 1 over r d over dr r, let me rewrite it properly, d over dr r d over dr minus 1 over r squared, because we can rewrite this second part, 1 over r squared d squared and d theta squared, in a different manner. We can rewrite it as minus 1 over r squared, since when we act with this operator on minus omega theta sine theta, since omega theta should not depend on theta because of symmetry, that will only act on the sine of theta. And therefore, when we take the second derivative of the sine, we get minus the sine. So we can put a minus here, and we can rewrite this operator simply as minus 1 over r squared, and then we get plus d squared dz squared, and this acts on omega theta without the sine, right? Because this operator will not act on the sine. This operator here will not act on the sine, and the only operator that acts on the sign, which is this one, we rewrote it in this manner, and in this case this is just a scalar which will not act on the sign. So this will give rise to this equation equal to 0. This is another important equation. So this one together with this one with the appropriate boundary conditions. So the boundary condition is that the velocity at very far from the sphere should be of this form. So the velocity is equal to 0, 0, u infinity. And also the following condition. So the velocity on the sphere, so let me write it as u of r, where r, capital R is the radius of the sphere. This should be the 0 vector. So the velocity should be 0 on the sphere because of the friction between the fluid and the sphere itself. The sphere is considered still, therefore the first layer of fluid which is in contact with the sphere should have a 0 velocity. So these are the boundary conditions that we have to use, and we will see this next time.